All right, welcome back. We are Game 2005 in the fall 2018 semester at George Brown, and we're week 6, actually week 7 equivalent, but less than 6. And we're talking about laws of motion today. But before we get into that, I just want to make a couple of announcements. One of them is the SDL template is up. So if you want to take a look at that, if you haven't seen that already, please download it, take a look at what's in there. Try and install it on your Visual Studio, make it a project or whatever. What I recommend is you keep the original one and you make copies of it. So if you want to have, we may do a tutorial or something like that, or a lab where I say, okay, take your template, make a copy, and then move from there. So that's what we're going to be using. We're going to be adding to that thing as we go. So please start it off and see how it goes, if it works on your system or not. I think we'd like to try and do that. So all the settings and everything else from a configuration perspective for Visual Studio is all preset for you. So that should all work out. Okay, so that's one thing. The other thing is I put up Lab 4 for this one. So I had to recreate the slides for this lecture. And the reason for that is when I first did them last year, they were insufficient. I didn't like them. There was something that was wrong with them and or missing. So I went through them again. They still need another pass. I'm just going to be honest, right? And it's all around the complexity of what we're talking about here. So I wanted to give you guys some more examples from the book. So that's what I did. I added more slides. Now, we don't have to go through every one of them, but I added some example slides in the back. They didn't exist last week. So if you downloaded your slides last week, then I've updated the slide deck. So please go up and download it again. All right. Again, we're sitting at week 7. By week 10, which is 3 short weeks from now, your assignment is going to be due. And by week 11, you'll have your test number 2. I know some people sent me some notes saying, are we having a midterm? So when I get that kind of question, it's like the person hasn't shown up to class or they haven't gone to tutorial or whatever. But remember, we're not going to have a traditional midterm or even a final. Our final is not going to be a traditional final because it's not going to build on everything that went before. It's going to be a unique little module that has nothing to do with physics, not really, necessarily. I'm not going to ask you physics questions. It's going to be a programming test more than anything else, right? So there'll be 3 parts. This is the second part. We're in the second module, and the second module will end on week 11 when we have our test, right, officially. Actually, not really. It'll actually end a little earlier than that, but that's when you're going to be tested on module 2. And then module 3 is going to be the programming module. We do collisions, which I think is going to be the most interesting part and the most difficult because of programming. People aren't good at programming. And it's actually synthesizing all the stuff we've done throughout the entire course. When you're doing stuff with programming to make it work, it's also some graphics. We're going to do 2D stuff, okay? So no 3D and SDL, please no. I don't want you guys to do an OpenGL context or anything like that, although that you can. So start playing with it. I recommend you download it and take a look at it, see if you can build something. I will provide a book on SDL as well, reference that I recommend you guys look into because it's some reading ahead in order for you guys to do that kind of stuff. It'll actually help you for next semester as well and next year because as you go through, we're going to do more and more C++. With SDL, it's supposed to be your main kind of, I would say your main framework. From a windowing perspective, and then you should be able to build on that. Okay, so that's that part. Let me get right into it because we have no time and lots of stuff to cover as always. So we're talking about the laws of motion this time around, and this is kind of the meat and bones of everything we do in physics. So here we're talking about Newton's laws. Newton was a famous dude. I don't know if there's a better way to say that. He really influenced everything in modern science today. Even though it says that he lived for a short time, and when he said the universal law of gravitation and stuff, it wasn't just that. It was all kinds of things that we use today, and we built upon Newton's studies and Newton's theories and everything else, and to create modern physics as it is. It's really cool. Now, there's limitations on Newton's laws, but these are enough for the most part to deal with most of things that happen in game. Okay, so again, we push things, we pull things. These are all forces, and we want to talk more about motion. This whole module has been about 1D and 2D motion, if anything. And even last module, when we went to calculus and trig, we talked about things like, the very simple kinematics, those kind of things. And simple kinematics, when we do a simulation or a game, can be very complex. So here's some examples of some stuff. You can have contact forces, lots of different kinds of forces. For people who've never done this before, please, this is for those people. For people who've done physics before, this will be a review, but this is what it is. You have contact forces, you have field forces. Field forces are things like gravitational fields, which we have no idea what they really are. We think they're some kind of distortion in the space-time continuum. I don't know, right? We still don't quite understand gravity. We have magnetic forces, which I think we understand better. We have, quantum level forces, weak and strong nuclear forces, and all kinds of other stuff. But the ones we care about are these ones, the ones that we can actually, kick and hit and move and collide with and all that stuff. These are the other ones. So gravitational force, electromagnetic forces. If you were going to be an engineer, definitely some of these you'd have to deal with, or most of them nuclear forces, and all these are field forces and they're out of scope. Okay, so we also can speak about a spring. A spring is a unique thing in that it has tension. And what it does is springs don't like to be deformed. Okay, so we have a spring, and if you push a spring together, or whether you pull a spring apart, right, it likes to go back to its original shape. Okay, actually, in reality, we have springy molecules all around us all the time. It's almost like we want to go back to the original shape more than anything else. You heat something, it warps, and then when you cool it, it goes back to the original shape. You cool it too much, it expands. As an example, or it contracts, sorry. And then eventually when it goes back to normal temperature or room temperature, it goes back to the original shape. We kind of spring in and out of these shapes. And a lot of people, what they do is they construct things, and if they're not used to doing things in engineering, they build something that they don't take into account the expansion and contraction of these due to heat and cooling, and things crack and break, right? So, but springs are funny in that we can actually calibrate them to get an idea of how much force there is that's being applied. The idea of force, it's a word that was created by Newton in many ways, or coined in his mind, how he meant forces. He's talking about forces. He wanted to use a better word than energy. It wasn't just about energy. And remember back then, their notion of energy, because they didn't have, electricity and all that kind of stuff that we have today. It was almost like the idea of, they had water, they had things moving, and they had motion a lot of times, and that's where they base these things. It's amazing for the little technology that they had, how much they understood. So we have this idea of a downward force. You can see that this is a force vector. So a force has magnitude and direction, which we're going to talk about. So you can see that if I take a spring and I elongate, I have a certain amount of force that elongates the spring with a similar tension to 1 centimeter. And if I make it go to 2 centimeters, there's obviously more force being used on the spring because it is deforming the spring a little bit more, right? And you can see that if you're in this situation where you're deforming a string at an angle, then you have two components of the force, a downward force and a force across the horizontal. And this is kind of something that we saw in 1D and 2D motion last week, where we saw the components of force, right? We didn't call it force, we call it X component, Y component, and motion in those directions. But we're going to use those same principles when we attack Newton stuff, right? So, except it's going to be more complex. Okay. So, this idea of an inertial frame of reference, when it comes to Newton's first law, I like to remember it like this: an object at rest tends to stay at rest, an object in motion tends to stay in motion. This idea that it'll continue to go forever, is interesting. If you're inside of an inertial frame of reference, and you're moving, but inside that frame, you may appear to have zero acceleration, although on the outside, remember we talked about frames of reference really quickly last week, and I said it's out of scope, because it's almost like how you perceive time and motion. So yeah, I'm just going to skip through this, some interesting reading, but it's nothing to do with us. It's more like what it says here. In the absence of external forces, when viewed from an initial reference frame, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity. So this is interesting because what this means is that when you're inside, let's say, for example, if you're in a microgravity environment like space and you have an object that's you've propelled, some kind of projectile in space, you're going to continue to move for the most part with micro, friction, in a straight line for a long, long time, right? And this is how space travel can work for us as we know it today, right? In that, we project something in a certain pathway, and it moves forward along that path, and it'll keep going and won't stop until it collides with something else. That's how it works. Okay, so that's really Newton's first law, and he starts playing with the idea of mass compared to weight, right? So remember we talked about a couple weeks ago. There's a difference between distance, and displacement. Now, we'd also talked about the difference between velocity and speed. There's notions of two different, kind of more vocabulary for us. And now we're going to talk about mass and weight. And for, again, people who've never understood these things, think about mass as more molecules, more atoms, the more stuff that makes up the universe. If you increase that amount in the same volume, so an object is denser, perhaps, or more densely packed, more mass, right? Then in the same gravity field, it would appear to have more weight. But it's not because, weight is not, there's a difference between mass and weight. Mass is to do with molecules and stuff, density, where weight is an effect of mass in a gravity, specific gravity. So again, mass is a scalar, right, as an example. So it's not something that has direction or magnitude. It has magnitude, but no direction. So that's the one thing. It talks about mass being an inherent property of an object. So if I was a superhero and if I had density manipulation and I could make myself denser or less dense, as an example, I could vary my mass, right? If I could do such a thing, impossible. But for now, but I mean, imagine if you could do that, you could vary your weight, you could float, if you can make yourself less dense and those kind of things, because the less mass we would have, I guess you'd turn almost insubstantial in some ways. It would vary how the effect of gravity would have on you to create this idea or notion of weight. And then we talked about this mass versus weight. So we have weight on the Earth. Example is 180 pounds. Weight on the moon is only 30 pounds, but mass in both places is 2 kilograms, right? So we have a certain mass, an amount of stuff that makes up the universe. We're made of star stuff, as people say. Physicists say, we're made of the stuff from the stars, our atoms and all those things and molecules. We recycle them, to make up who we are. But that stuff that makes us up, that is going to be the same amount approximately on different places. But because of the gravity field, call it whatever you like, the intensive, the effect of gravity in different environments, you're going to appear to have a different weight, right? So on the moon, which is 1/6 Earth's gravity approximately, right? You're going to feel, 1/6 the weight than you would on the Earth. And this could, produce problems for us going forward. If we want to, populate the moon and we have some kind of dome, I picture like science fiction, dome on a moon, and you're living on the moon, you're a lunatic, quote unquote, on a moon, living there for a long time on Luna. And then you want to come back to Earth, it's going to be a problem, right? It's going to be a problem because your bones and your muscles and everything about your organs are going to be used to this less, lower gravity. And there's some thoughts, some theories, and actually it's coming to pass as well, especially people who've lived on the International Space Station. They do a lot of exercise and they come back, especially when they live, they're there for a long time in microgravity. So it can have a real effect on stuff. And in the future, whether we go to Mars or whether we stay on the moon or whatever, this idea of gravitational forces affecting us is going to be really much more apparent. So interesting stuff, and I love science fiction, so I always kind of think about those things. Yes?
How can you measure mass without the gravity?
That's a good question. A lot of times it's, we have a challenge doing that, right? Because we see volumes, right? So if I see two people, so I see a bodybuilder, right, as an example, and, and another person who's not a bodybuilder next to that person, right? One person's lots of dense muscle, and the other person's not so much dense muscle. They might weigh totally different, right? Muscle weighs more than fat, let's say, so you have densely packed muscle, so higher mass, right? More because there's a lot more material inside there than, let's say the other person. It's hard for you to measure them. When you look at them, they look the same. So by eye, it's hard to see that, right? But they have tests where they actually can look at volumes, and they do scans and all those kind of things. Like you can see densely packed material with things like MRIs and those kind of things. But when it comes to total mass, it's hard. It's really, really hard. You have to analyze the material that makes up an object. How do you do that, right? Without killing the object, like a human being. That's the reason why we don't have teleporters, right? I can't scan the crap out of you to figure out what you're made of, right? If I do, you're dead, right? I might clone you on one hand, but you'll appear like a photocopy that's dead, inert, right? So, anyways, but yeah, there's other ways of doing it. Scientists have figured out a way. We can figure out how the volume of an object, through displacement, right? We put it in water, right? You figure out the total volume of an object, in a regular object. But that doesn't really speak about mass. It just speaks about volume, right? So just because an object has a lot of volume doesn't mean it has a lot of mass, right? A good example is a neutron star or something like that's got that physicists and astrophysicists have looked at. They see two stars. One has a much smaller volume, but a much higher mass, and it warps the fabric of space a lot more with a small mass, right? Because it's densely packed particles that have kind of collapsed into a smaller space, higher density, right? Bigger mass, lower volume. So that's kind of the hard thing to talk about. Okay, let's move on. So Newton's second law. So the first law is an object that is at rest tends to stay at rest. An object in motion tends to stay in motion. Nike uses that kind of stuff all the time, saying, "Work out, just do it. Keep in motion, and you'll stay fit." This idea. And so physics goes to this metaphysics idea, right? But Newton's second law is more practical for us. It says, really, in a nutshell, force. They make a relationship between force and mass and acceleration. Where I want to find the total amount of force in units, right? How much force, this idea of force, they want to measure it. And they say, well, force is equal to our mass times some kind of acceleration, right? Make this relationship. And force is measured for this part of our course in newtons, for the most part, okay? Newtons. It's just, Newton had to do something, right? So, he created his own unit, newtons, right? And so when we see N, it means newtons, and it has a relationship between, it talks about the number, the force. Force is not a scalar, force is a vector, because it has magnitude and direction, okay? And you can see here that we have forces across different axes, X, Y, and Z, right? As an example, and we know that the sum of all forces, this is how we say it, see that little sigma there? I'm gonna say this a lot today. Which is the net force, the sum of all forces across the x-axis. So sigma, the big sigma with F and a little axis symbol down here, is equal to the mass of an object across and times the acceleration across that x-axis, as an example. So it can't just be some acceleration, it has to be acceleration across a particular axis as well, right? Well, we take all these forces and add them up until we get a sum of forces in a particular direction. Right. So again, when we add X, Y, and Z, we have an angle somewhere in three-dimensional space. The resulting net force is the thing that pushes an object or pulls an object in a particular direction. So this is kind of a key, going back to this kind of a key formula we're going to use a lot, force equal to ma. And this talks about newtons. 1 Newton is 1 kilogram meter per second squared, right? If that makes sense. So 1 kilogram, that's mass, and then times acceleration, meters per second squared. So you can say that 1 Newton is 1 kilogram meters per second squared, meter seconds. There's also something called the slug foot. That's interesting. I always love that one, right? It's a US thing. 1 pound is 1 slug foot per second squared, right? 1 slug. You're a slug, man. There's a slug in the States already. Anyways, let's keep going. We have Newton's second law as an example. Now, I put this in. This is what I put in recently because I wanted to talk about this. So you have, this is where it becomes complex. I have a hockey puck as an example with a mass of 0.3 kilograms. It slides on the frictionless horizontal surface of an ice rink. When we say frictionless, that means there's nothing to stop it. There's no other opposing force to stop this hockey puck. Is ice really frictionless? No, it's close, but it's not completely frictionless. If it was, then you couldn't skate, right? So 2 hockey sticks strike the puck simultaneously. So you can see one strikes it this way, as an example. Another one strikes it this way. Where is it going to go? So the force F1 has a magnitude of 5 newtons, 5 newtons, and is directed in theta is equal to 20 degrees. So this degree, from the horizontal, as an example, right? And then, the F2 force, right, has a magnitude of 8 newtons, so higher magnitude. So, maybe this stick that hit this puck was, struck way faster. And its direction is theta is equal to 60 degrees from the horizontal, right? All right, determine both the magnitude and direction of the puck's acceleration. So just before you look at the slides ahead, what do you think? What do you think we could do here? Like, how do I figure out the total, the new vector that I'm going to go into? Because this is what's going to happen in your games, guys. You're going to have something that hits something else, and you're going to have a resultant vector maybe, right? So what's the resultant vector? I have a force this way, and I have a force this way. Where am I going to go? Right, somewhere in between, right? That's what's going to happen. The question is, where in between? And how do we figure that out? So we know, before we move on to the next page, we know that if I have a force, it's made up of mass and acceleration. I have a mass, which is 0.3 kilograms, right? And I'm on a surface, right? So what is my acceleration? If I was going to find out the acceleration, that's what it's asking for, right? So I have force and I have mass, I can find acceleration, right? Because I have a relationship. I can just do a little bit of algebra, move things around, right? And I know if I have a puck that's 0.3 kilograms and 5 newtons of force, then that means that my acceleration is my force in newtons over mass, right? Acceleration is force over mass, right? So 5 newtons over 0.3, and that gives me my total acceleration across in one direction, right? However, that doesn't tell me anything about, the net forces. Because they're at an angle, we have to break our forces down into their components, right? So F1 here has two components, the X component and the Y component, to create this force in this direction. And then we have F2, which has, the X component forces and the Y component forces. And what we need to do is do some vector addition, seriously, and add the component forces together to get the total net force across the X-axis and the Y-axis to produce our new vector. That's what happens, right? Okay, so how do we do that? So first we want to conceptualize. Again, the acceleration of the puck will be in the same direction. And then it says, and by the way, I ignored these things a lot more in the last couple of lessons, but this one is hard to ignore. Please read these if you have a question understanding what's going on. Well, one of the things that we go into is this analysis stuff. So we sit there and go, okay, well, look, the sum of the forces across the x-axis and the sum of the forces across the y-axis is what we want. So we take F1x and F2x and we add them together, right, as an example, and it's equal to F1 cos theta plus F2 cos phi, right? Now we just use another indicator for the second angle. But at the end of the day, why would this be? Because we go back to what we did last week when we did motion in 2 directions, where we said across the x-axis, when we have some kind of angle, you don't have all of the forces, all the energies directed in that direction. It gets sapped away by the angle. So depending on the angle of attack, right, you have less energy going in a certain direction than you would normally have. If I had 100% of my energy going on the x, that means I would have 0 on the y, right? And my angle would be at 90 degrees or something like that, right? In this case, it's not true, because if you look at the original one, if we just look at the force, the vector F, right, F1, you can see that there's this F1 force, and if we looked at it, it has 5 newtons. So 5 newtons of force. Okay, so we have some kind of force in this direction. Think about it as velocity, just like we figured out velocity last week when we said v cos theta, right, for the x-axis. Now we use f cos theta, right, where we have a total number of force in newtons, and we have some part of it is directed in the x-axis, and some part of the energy is directed on the y-axis. When we add those two forces together, both for F1 and F2, and we have this resultant force, these formulas here. So the sum of all forces across the x-axis then would be F1 cos theta plus F2 cos phi, and the sum of all forces across the y-axis is equal to F1 sine theta plus F2 sine phi. Notice that sine is associated with y and cos is still associated with x, right? And then we have this idea of acceleration. We want to find the acceleration, and we know that acceleration is equal to force over mass. We just talked about that, right? So force over mass, the sum of all forces across the x-axis over the mass of the object is the total acceleration across that one axis, right? And so we can break it down like this, which is pretty straightforward. This is, by the way, the most simplest problem you'll see, all right? But it's pretty straightforward. Then we sub in the numbers, right? So we say 5 newtons of force times cos of minus 20 plus 8 newtons times cos of 60 over 0.3 kilograms is equal to 29 meters per second squared. That is the acceleration across the x-axis. And then we have the acceleration across the y-axis. And then to find the total acceleration, we use Pythagorean theorem, right, where c squared is equal to a squared plus b squared, to give us the total resultant force, 34 meters per second squared. That is the magnitude. Now we need direction. So, so what we do is we take the ratio of y over x, right? So sine over cosine, which is tangent. And we want to take the inverse tan, or the arctangent, of this acceleration on the y-axis over the acceleration on the x-axis to find the total angle, which is 31 degrees. Okay, so that's how you do it. I put these in the slides purposely for you guys to use as a reference, right? Because you have to have a look at something to give you a hand on what to do. And remember what we're doing here. What we're doing is we're saying that, hey, there's these two vectors that are pulling me in two different directions, right? Whatever those vectors are. I'm being pulled in this direction. I'm being pulled in this direction. Which direction am I going to go in? Depending on how much force is here or here. Let's say these two cables that are holding that are drawing the centralized force or centralized mass are strong enough so they won't break, then it's going to go when we add the vectors together in a particular direction. Yes, of course. They don't know that I'm teaching. Gravitational forces is another thing. It's something that we're going to be talking about a lot. So sometimes when we say that force is equal to ma, a lot of times for Newton's laws, we mean that force is equal to mg, where g is equal to gravity, force of gravity. The magnitude of gravity is on Earth is 9.8, and the direction is downward, right? So a lot of times we have this downward force of gravity, and we mention it like this. We have a subscript force, the force vector, usually, and small g, gravity, is equal to mg. And usually we have a vector here, I didn't write this in, and a vector across the gravity. And you can see that that's how it's written here. Remember the vectors, little lines on top mean a vector. So you're going to see that a lot. One thing to note is more about units. Kilogram is not a unit of weight, but rather a unit of mass. So how many grams of matter do we have inside of an object? The stuff of the universe is what I like to say, right? Okay, which we talked about earlier. I'm going to keep going. So Newton's third law. Newton's third law says that basically this is weird. I don't know why it's all skewed here, but yeah, let's see if I can move this around. It's skewed, right? So we have this force 1, 2 exerted by an object 1 and object 2, force 1, 2, right, is equal to the magnitude, position, and direction to the force F21 exerted by object 2 on object 1. In other words, if you were going to break this down and say it differently, here's another way of saying it. An action force is equal in magnitude to the reaction force in opposite direction, equal in opposite, force. So you have a reaction, if you will, right? Where you have one object hitting another object, and they're imparting an amount of energy on each other, and they're going to go back the other way, right? They're going to hit each other, an opposite and equal reaction, right? That's what's going to happen. So those are the three laws. Three laws are, and if you're going to ask this on a multiple choice question, you should know what they are, which is an object at rest tends to stay at rest, an object of motion tends to stay at motion. That's first law. Second law is force equal to ma, right? And third law is, this idea of, when you a force, when it hits something, you get this opposite and equal reaction, to two objects that are hitting each other, right? Which is kind of interesting. There's another way of saying that that's probably a little better than I just said it. Okay, so you have this idea of these two objects exerted on each other. I have this object, with, let's say, object 1 with force 2-1. Force 2-1, sure. And object 2 with force 1-2, and they're kind of going this way, and this one's going this way. And you can see that you take the first one, F12, and subtract it from the second one, and they're equal to. They're basically equate to 0. In fact, when you add them together, F12 plus F21, they produce 0 force together, right? Those two things equate to 0 because they have equal and opposite reactions. This is assuming that the masses are equal, right? Although it doesn't look equal here. Why is that? Because if I have more mass and I'm accelerating at the same rate, then I have more force, right? More mass, same acceleration means more force. We talked about this way earlier on when I said, Newtonian physics are the thing that keeps us from understanding how we can accelerate to the speed of light in a vacuum. Can't do it, right? Because we know by Einsteinian laws, Einsteinian physics, that as we move towards the speed of light, our mass continues to increase. The way we measure our mass continues to increase to infinity, right? It's almost like we gain mass somehow. We gain energy as we move towards infinity. And in order for us to push this faster and faster, it takes an infinite amount of force, which I don't know anything. There's not, all the stars in the universe can't add up to the infinite amount of force for us to travel to the speed of light, right? So therefore, faster than light travel using Einsteinian physics is impossible, right? And this is an idea of that because we have these forces being exerted, and the more mass there is, the more force that's required to move it. Okay, so pretty simple concepts, but it can cause more complex problems. One thing we're also going to be talking about is this idea of the normal force, where a force is pushing back up at you, right? Especially on an immovable object, right? And what I mean by immovable object is something that's pretty hard to crash through, right? So if I was strong enough to push down on this desk, right, with one hand and just crack it, right? So I push down on it and crack it. Then the normal force of the desk wouldn't be strong enough to support my mass, right? It wouldn't be able to oppose the amount of mass or energy that I'm putting down on the desk, right? So normal forces exist everywhere, right? You have a car on a road. The car doesn't sink into the street, right? The normal force pushes it back up. A train on a railroad track, right? As an example, the rails are able to sustain the train, to support the train. There's a normal force that's pushing the train back up, even though it's very heavy, right? So this idea of normal force, also a boat on in the sea or in the water or somewhere, right? The buoyancy force, which is the equivalent to the normal force, pushing the boat up, right? It's pushing the boat up and it's countermanding the force of gravity. So gravity is pulling you down all the time, but normal force is pushing you back up. And we can safely say for most circumstances in our little course right now, right, that the normal force is going to be equal to the force of gravity when it's perpendicular. So if I'm standing on the ground here, if I have a certain amount of mass, the normal force, which is underneath my feet, is pushing me up, while at the same time the gravity is pulling me down, and those two forces are in equilibrium, right? So I'm not crashing through the ground, right, in this particular case. Okay, so this idea of normal force. And the idea of normal force gives rise to other things, which we'll talk about in a second. So I have these two objects. I have a monitor on a desk. I have the normal force, right, as an example, and I have this force of gravity that's pulling me down, right? And they're in equilibrium, okay? We're going to start talking about this idea of a free body diagram. And for your assignment number 2, one of the things you've been asked to do is draw free body diagrams for some of the situations that I presented, right? When you draw a free body diagram, think about all the net forces applied to the center of a mass of the object. So for example, in one of the questions I say, draw a free body diagram for R2-D2 as he's going around, a Ferris wheel, right, at different points. Well, at different points, how am I going to draw a free body diagram? R2-D2 is like a 30 kilogram mass is what I put in there, or something like that, right? And especially when it comes to irregular masses, it's hard to kind of pinpoint where the center of mass is, because the object might be droopy or irregular. In our cases, and for your guys, in most video games that you're going to make, right? Unless you're going to make some kind of squishy object in your video game, the object of, the center of mass is going to be the direct center of where that mass is, approximately, right? Now you can change that to give your object's weird motion effects or whatever, but at the end of the day, it's going to be in the center, or direct center. So we look at the direct center, it's going to be represented by this dot. So the dot represents the center of mass, right, when you draw your free body diagram. Then you're going to have all the forces on it, the net forces. The force of gravity most likely is going to pull that object down. And then you're going to have the normal force, chances are, pushing that object back up. So you're going to have those two forces for sure. And they're going to be equal and in opposition, right, typically. All right? This is when an object is resting on another object. If the object is not resting on another object, if it's in free fall, there's no normal force, right? Because now the force of gravity is taken hold, and it's going to pull an object right into the ground, right? Until the object hits the ground, and where then there's going to be the normal force is going to spring up again because it's being held to the ground. Sometimes the object will fall into the ground because it'll penetrate some distance before the normal force can take hold and stop it from moving. But at the end of the day, there's going to be most likely these two forces when an object is sitting at rest. Okay, so we have this idea of a particle model that we've been using, and what we want to try and do, we have to make some assumptions in this course, especially for this part, which is objects can be modeled as particles, number one. So that means that there's no real irregularities, right? It's not like the object is like imbalanced on one side or the other. It's not squishy, it's not made of air on one part and the other part is made of matter, right? It's not like that. It's like a contiguous mass, right? We're only interested in the external forces acting on the object. So we don't care about the reactionary forces or the internal forces that are pulling an object apart, right? So we don't care about those things, or squishing an object together, not really, okay? And initially we want to deal with a frictionless surface. Anything we talk about is all frictionless. We may talk about friction, we're going to talk about it today, later on, but for initially, these are the situations. When it comes to something that's holding another object up, a string, a rope, a wire, the masses of those objects, the actual wire itself, we're going to ignore. Okay, so we're not going to take into account the mass of the wire, because there's also that factor as well when it comes to engineering. All we care about a lot of times is the magnitude of the tension on that wire. A lot of times, how much tension, the force that's pulling that wire, how much force is there on that wire or rope or string? That's typically what we care about. Are we good with that? So again, we're making some assumptions because we're trying to simplify a system from an understanding perspective. And in games, you're going to do the same thing. You're going to take your potentially complex physics problem and simplify into something that you can eat, something that is digestible for you from a problem-solving perspective, right? Once you start going to something that's really too complex, then how are you going to model that with code? How are you going to do that? It becomes almost like I'm going to fudge it, and I'm going to put these placeholder values, and then it's just going to do what I want it to do. And a lot of times that's what we do, right? But that may not be as realistic when it comes to motion as we'd like. So we have this idea of this particle in equilibrium, where sometimes we have these two forces that are kind of moving against each other. When a particle is in equilibrium, that means that the sum of all forces is zero. So when we add all the forces in different directions and all that kind of stuff, we don't have a particle that's moving. It's just sitting there in the middle. So that we can say that that particle is in equilibrium, right? We'll see some examples of that in a second. Here's one of them. So I have this lamp. It's hanging from the ceiling, right? And the lamp that's hanging from the ceiling, right? It's not going to fall. that projector that's sitting on top of you right here, right? If it wasn't in equilibrium, it'd fall and kill you, right? I'm saying it would chop you in half. I'm joking. Right? It would eviscerate you. No, I'm joking. It doesn't have that kind of. There's no sharp spikes on the projector. Don't worry. But at the end of the day, what I'm saying is that you have objects that are in equilibrium. You have this lamp as an example. It's not going to fall. Why? Because the tension of the wire and the fasteners that fasten the lamp or whatever it is to the ceiling are strong enough to oppose the downward gravity, right? As well as the wire, if you think about this, the tension, T, we can say, is equal to the tension F of G, right? Where force of gravity, right? So the force of gravity is pulling down, the tension is pushing up, right? And those two things, we can see them as they're in equilibrium. This formula is the equilibrium formula, which we're going to use over and over again. We're always going to think that we're going to subtract gravity because gravity is in a downward direction from the tension. Okay, so tension minus gravity, 0, because we're in equilibrium. If the lamp was falling or moving slowly down, right, because of gravity, and the tension wasn't holding it, and I don't know, maybe the cable was slipping or something, it wouldn't be in equilibrium. But for most of our cases, it is. All right, so the first thing we want to do is draw a free body diagram to understand how Newton's second law can take hold. Here's another example. We have this example of this person who's dragging a crate as an example, and we want to draw a free body diagram. How does it look? Well, we have the normal force. Here's the normal force. And we have this force of gravity, right? And then we have this tension, right? So do we care about the force of gravity or the normal force at the end of the day? If this object was being pulled along a frictionless surface, then all we care about is T, the tension T, or along that x-axis. Okay, that's all we care about, because the force of gravity and the normal force are canceling each other out. Okay, does that make sense? So the free body diagram would look like this: normal force up, gravity down, tension along a certain direction. Okay. Okay, and then we have, here's Newton's second law as an example. The force, sum of all forces across the x-axis is equal to T, the tension, which is equal to mass times acceleration across the x-axis. The sum of all forces across the y-axis is equal to, and this is where we use the equilibrium formula, right? The normal force minus the force of gravity, which is equal to 0, right? And we can say that the normal force is equal to the force of gravity, so we don't care about the force, the sum of all forces across the y-axis. We only care about the sum of all forces across the x-axis. And if the tension is constant, then the acceleration is constant, and the kinematic equations can be used to more fully describe this motion. So the ones we talked about last week and the week before. Okay. Here's another one. So we have this idea of some kind of force. I'm pushing down on my physics book here as an example, and I have also, if I was going to draw the free body diagram, it'd be drawn like this. I would have the physics book. I have force coming down plus this force of gravity, because I'm pushing down, but there's also a force of gravity pulling the book down too, right? However, it's on a table that's strong enough, the normal force is strong enough to repel the force of gravity, 10 meters approximately per second squared, plus whatever force I'm putting onto it. The normal force is equal to those things, can equal or countermand or repel the energy that I'm putting into onto the table. Now, if I sat on the table and on the book, right, or if I jumped up and down on it to produce additional momentum, right, then maybe I could crack the desk, right, and I can countermand the normal force that it would produce, and I would go through it, right? But then I would land on the ground, and the normal force would take hold again, right? The normal force, by the way, this is interesting. When we talk about in CG, computer graphics, when we talk about the normal, it's perpendicular to the face of the object that we're talking about, right? So notice that here our normal force is pushing up. It's perpendicular to the surface, right? So it's perpendicular. So the normal on this screen, right, is coming perpendicular up from the screen this way, right? We do polygonal modeling a lot of times, like for example in Blender. The normals are looking away from the faces typically, right? Okay, that's an interesting fact, at least for me. Some of you are like, it's 8 o'clock on a Tuesday morning, and I don't feel like being here, which is totally typical. So yeah, so Newton's laws, we talked about, move on here. And it talks about how to do the free body diagram. Okay, here's example number 2. And I put this in more detail. Now, this is more of a difficult problem, all right? When you first look at this, you're like, well, maybe I can solve this with 2D motion, right? I can solve this 2D motion. I can kind of figure out, you know, it's triangles. I'm good to go, right? Problem is that we don't know what the angle is here. We have theta 1 and theta 2. If theta 1 is 37 degrees and theta 2 is 53 degrees, right? And just by chance, this equates to 90 degrees. What's left? 90 degrees, right? So 90 plus 90 is 180. So you know this triangle is equal to 180 degrees. But however, we have this line, this imaginary line that goes up from this little point here, the knot, all the way to the top, where you have 2 angles, right? And we don't know how much of a split there is. We don't know how much this angle is being split, that 90-degree angle. Is it 45 and 45? No, can't be, because you can see that it's drawn so that there's more energy in one direction than there is in another. More energy in one direction than there is in this other direction, right? Also, the cable lengths are different, right? So it's hard for us to figure this out. How do I can't just chop it up in different triangles so easily, because it's just more difficult for me to do. So what do I do here? How do I figure this out, right? Given this information. Well, I've been given that this light weighing 122 newtons. That's kind of a weird thing. It weighs 122 newtons. And sometimes you might get this problem as well. I put this down in the PowerPoint so you guys can see sometimes what kind of questions you're going to get on your test in a few weeks, right? So when I say weighs 122 newtons, it means that it has 122 newtons of force down, right? And that means that the force of gravity on this object is 122 newtons, okay? So if I know the gravity is 9.8 meters per second squared in the downward position, I have force, I have acceleration, I want to find mass, I take force over acceleration, equates to my mass, whatever that mass is, right? And that's how I can figure out the mass, by its total, you know, the force of gravity, it being a number of newtons. The upper cables make this angle, and it says that these upper cables are not as strong as the vertical cable that holds, not as strong as this one, and will break if there's more than 100 newtons of force in either one of those cables. Are the cables strong enough? It's an engineering problem. Are the cables strong enough to support the traffic light? How do I figure that out? So now, what the heck do I do? That's the question that you're going to ask yourself. Number 1, draw a free-body diagram. Number 1. Draw all the forces in all directions that you can understand. Well, we know, before I go to the next page, that we have gravity pulling down from that knot. If you look at that knot as the center of mass of this whole system, right? The force of gravity pulling down from that knot, as an example, is one of the forces. Okay, yes?
Should we split the free body diagram into 3 parts then for all 3 cables?
No.
But how would you figure out the individual forces in cable then? One triangle.
Bear with me. Yeah. So you have this force pulling down on the knot. Think about the knot as the center of mass, okay? And I have this other force pushing this way and this other force pushing that way. Well, guess what? I have component forces pulling me this way and pulling me this way. I know that this system is in equilibrium. I hope that this system is in equilibrium, right? And if this system is in equilibrium, if I can think of that, right? That means that the sum of all forces across the x-axis and the sum of all forces across the y-axis, when you add them together, provide, you know, are equal to the force of gravity that's pulling this object down. We make that assumption. Let's take a look. So now we split this up. We say, okay, we want to conceptualize it. We're going to start drawing angles and all this kind of stuff down. We kind of put together these tensions. So T1 is this tension, T2 is this tension, T3 is this tension. These are just tension forces. So when we say T is tension. So the net force on the knot is 0. These are things we've started to categorize. The particle in equilibrium, this is the particle. We think about the knot as the particle that's being moved, the central area right here. And we construct this diagram. So we can say that the light has some kind of force of gravity, and this T3, the force of gravity and this tension are the same, right? Because this is strong enough to command the force of gravity. All right, so we have this now. We broke it down into this kind of situation. And notice we put this horizontal line that goes like this. But that's not how it was drawn, right? The original diagram, if you look at it, was drawn like this. right? And we said that there is theta 1 is 37 and theta 2 is 53. Then we drew this. How do we do that? Because of trigonometry. We know that there are equivalent angles. So this angle here, as an example, is equivalent to this angle down here. This angle here is equivalent to this angle down here, right? So these angles here are equivalent, this one here and this one here, this one here and this one here, right? So we can draw an object like this, so it's easier for us to understand. Now it's a hockey puck question again, right? Before, it was something that looked unrecognizable, but now we've made it into like two forces going in a direction, another force is dragging the other way. You know, how much tension do we have? Okay, and then we start thinking about this. So we start analyzing all the forces across the y-axis must be zero, right? The one that goes up and down, because the traffic light is not moving, right? It's not falling down. If we said the traffic light's falling down, we know that the forces across the y-axis are not zero. It doesn't equate to zero. The sum of all forces. When we say the sum of all forces, that means the force pulling down and the normal force pulling up, right? Those things must be in equilibrium, right? So we can say that then that the T3, which is the tension on the wire, the third wire, the one that's going down, minus the force of gravity always pulls down, must be zero. Therefore, T3, if you move this around, is equal to the force of gravity. Tension is equal to the force of gravity. Which means tension actually is equal to whatever the force of gravity is on that mass. Now we break down the force in its components. We say tension 1 is minus T1 cos theta 1. Okay, why do we say that? So why do we say minus? Because this is in the left side, right? On the left side, everything to the left is negative on the x-axis. So therefore, it's a negative T, T cos theta, right? Because on the x-axis, because you're going left is negative, to the right is positive, up is positive, to down is negative, right? So now we start putting directions on our vectors, right? Okay, let's keep going. So we see that, so T1 on the x component is negative T1 cos theta, where T1 is the total tension across that line, right? And then on the y component is T1 sine theta, right? Why is it positive? Because it's going up, right? And how do I know that? If I look at the diagram, you can see that this is the y component of this part, this tension wire, right? So we have this force going this way. We have x component and y component, and the y component is positive. The x component to the left is negative. Your left, negative, right? And then on this one, we have two positive forces. The x component here is positive, and the y component here is positive, right? So that's what we see here. T2 cos theta 2, T2 sine theta 2, just like we did last week with two-dimensional forces, right? T3, though, on the x component, is there any gravity happening on the x component? There's no acceleration going either one way, so T3 on the x component is zero. We don't have a force. The sum of all forces on the third tension wire is zero on the x-axis. However, on the y-axis, we have this negative force of gravity pulling us down. We have that. Okay, so we've kind of put all those things together. And then we apply the particle and equilibrium model to the dot. We say that the sum of all forces across the x-axis is equal to negative T cos theta 1 plus 2T cos theta 2, and that equals to 0. Why is that? Because, going back to this model again, the knot's not moving this way or the other way. It's not swaying. It's staying in the middle, which means both forces on the left side and on the right side must be in equilibrium, right? That means that if I add the negative forces here on the left to the positive forces here on the right, they're not going to move anything. It's going to equate to 0. Same thing with the positive negative forces across the y-axis. So if you see that negative T cos theta 1 plus 2T cos theta 2 is equal to 0. And the same thing goes with on the y-axis. T1 sine theta 1 plus T2 sine theta 2 plus a negative force of gravity, all that together is equal to 0, right? So we have sine theta 1 and sine theta 2. So sine theta 1 plus sine theta 2 on this side. So I'm using both sides, 1 and 2, these two sides. Those can, both those forces across the y-axis, when you subtract gravity, that whole thing equals 0, right? Are you good? Yeah.
And because this is the line of the forces, like in the next slide, you can T3 for F3 in the case of climate.
Yeah. So again, you notice that the right the left side of the sign that we're talking about on the y-axis. Yeah. Oh, here. Yeah, because T3, because it's just the y component, right? It's the y component. So when we say the total forces on T3, right, the tension wire, on the x component is 0, right? There's no forces. The total sum of all forces across the y-axis, though, is equal to the force of gravity. And the force of gravity, we have to have a sign for it, which is negative, going down, right? That's what it means. So I understand what you're saying. You're saying that how come we just can't say it's just Fg, right, as opposed to negative Fg. That's what we're saying here. We're saying T3 is equal to Fg. We're talking about the total tension, but there's no direction. See, we don't have a force vector. We just have magnitude. This is just magnitude of all forces. Sorry? It's the magnitude. Magnitude is an absolute value, right? We have a magnitude, but we don't have a direction. Remember, a vector has both magnitude and direction. Here, we're just saying that the magnitude of all forces across the T3 is equal to the magnitude of the force of gravity, right? Not a direction. That's why there's no arrow on top of this thing. It's not a vector here. We're just talking about magnitude. All right, so that's what we can equate. We can put these two equations together, and there's a little bit of a note there that explains that. Okay, then we start subbing things in. We say that, well, let's put solve for T1 in terms of T2. So we just move things around. So going back to this one, we take number 3 and we move things around so that we put T1 in terms of T2. So we'll put 2 on one side and we have T1 on the other side. Okay, so that's what we've done here. So we've taken T2 on one side and we've created an equation for T1. So T1 cos theta 1 over cos theta 2, that equals to T2. Okay, once we have this, then we substitute this value. So any place we see T2 in the second equation, we sub in the first equation. Now what we're doing is we're taking 2 equations and 2 unknowns kind of thing. We're solving a system of linear equations. What we're trying to do is we're going to sub things in so we can eliminate one of the unknowns, which is T2. We're just making it in terms of T1, notice in this particular equation. And once we've done that, we can solve for T1, which is equal to the force of gravity on the top, sine theta 1 plus cos theta 1 tan theta 2, because if you once you multiply sine theta 2 over cos theta 2, sine over cosine is tangent, right? That's how you got tan theta 2, right? And then we multiply by cos theta 1. That's the one part. And then, but we want to isolate T1, which means when we do some funky algebra, we get to this. Okay? By the way, guys, this is a pattern, and I fully expect you guys, when you get your cheat sheet, if you want to move things around and put some patterns on your cheat sheet for test number 2, totally fine to do that, right? Because how are you going to remember all this stuff, right? You may not. But the thinking is what we want to talk about more than anything else here. All right, then we start substituting in the numerical values. We know that the force of gravity is 122 newtons because the tension on line 3, right, is 122 newtons of force, right? Then we substitute sine 37 for theta 1 and cos 37 for theta 1 over here, and tangent of 53 for theta 2 here. And when we solve everything, we get to something like the tension on line 1 is 73.4 newtons. Now we know what we were told, that we cannot have a tension of 100 newtons on any one of the wires, or the traffic light will fall, right? It won't be supportive, right? So we know that 73.4 on, at least on this axis, so if we go back to the example, we know on this part of the traffic light over here is strong enough to support the traffic light, this tension wire, right? How about the other wire? So we can see that T2 then, once we know what T1 is, we can substitute T1 into the equation for T2, right, which is this one up here. And we get cos 37 over cos 53, and then you come up with 97.4 newtons. Guess what? That's almost enough to snap the wire. So maybe what we want to try and do is make that, the tension of the wire more than 100 newtons, right? Because we're very close here. A little bit of a wind, something else, right? A fraying of the wires, and that thing is gone. It's going to fall, the whole traffic light, right? Or it's going to swing anyway, right? So that's not cool. So if you think about that, and if it swings, then T1 is going to hold the whole tension, the whole 100 and X number of newtons, we said, 122.
Or more because it's swinging.
And more because it's swinging. So what's going to happen is when that goes on, it's the other one's going to snap. So it's going to happen. It's going to be like this. So let's say the wind happens as an example, and then this one snaps, and this one's going to swing, and now this is supporting everything, and this one's going to fall. That's what's going to happen very quickly, right? Because of the way this thing is built. So we don't want this situation. And so if I was an engineer, I would say we're pretty close. Our tension's maybe too close. You know, within 10%, I'd recommend, you know, moving it, you know, to a stronger cables, right? So does that make sense? Is it strong enough to hold right now? It is. Should you leave it this way if you're an engineer? Probably not. I don't recommend that, right? And I don't know what the safety standards are, but it's probably like twice. I'm telling you right now, because it's like you don't want to leave it so it's like this close. Are we good with these kinds of things? So we have a set of formulas, and look, what we're using is equilibrium and Newton's second law to kind of formulate this object in equilibrium. And this is where the challenge is when it comes to problem solving. How do I draw my object? How do I conceptualize? Before, last week it was kind of easy. We just kind of drew our diagram, put our forces together, and hey, we're fine. Nowadays, but this time we're like, wait a minute. I got forces from all kinds of directions here. What do I do, right? You got to draw your free body diagram. That's the first part. All right, so again, normal force acts perpendicular to the plane. Gravitational force acts straight down. This idea of stuff. And it works for inclined planes. Inclined planes is one of the questions you have on your assignment. You have this loot crate. It's falling down a, you know, some kind of slope, as an example. And how far does it go? We can look at it the same as a runaway car. So this idea of this car, it doesn't have its parking brake on, and it's left to roll down a hill, right, as an example. And the car of a mass M is on an icy driveway, inclined at an angle, you know, theta. Let's say it's in park, sure, on an icy driveway. Find the acceleration of the car, assuming the driveway is frictionless. Do we care about the mass when it comes to the acceleration? We do, right? Mass times acceleration is a total force. But in terms of motion, right? Think about that. Does a heavier object accelerate faster than a lighter object? No, right? So this is where the mass of the car becomes moot. We don't care about it. So we don't care about that at all. We care about angle theta, though, whatever that angle theta is. One of the things you notice is that when we start drawing our free body diagram here, we're drawing it at a weird angle. And I'm going to talk about this as a point of solution. So again, we categorize the car. We start thinking about it. That's what this idea is. And then we get to this analysis phase, and then we see this. Now, typically, some students would draw it this way. So normal force is up this way for some reason. But that's not right, is it? Normal force is perpendicular to the plane of action. So the plane of action in this particular case is this way, across the slope, up, right? And this is where, for the first time, we're going to see the x component across this particular oriented plane. So the plane, instead of it being the horizontal, is now at an angle, right? Once you have that situation, remember we talked about cos theta, you know, v cos theta for x and v cos, v sine theta for y. It's reversed when it comes to an inclined plane. So if you notice that, we have the normal force, right? And we have the force of gravity. It's coming down at an angle this way, right? Because gravity goes straight down. The normal force goes off at an angle. Now we have a resultant vector that's going to take me this way somehow, right? Notice that the normal force and mg cos theta, which is the y component of gravity, right, as an example, or the normal force here, is in opposition. So what's left over is mg sine theta. Mg sine theta is what's dragging our car down the slope, right? So mass times gravity times sine of the angle, whatever that is the only thing that's dragging us down. That's the only force that's not in equilibrium. The other forces are all in equilibrium. Why? We've broken down the force of gravity now for the first time, right? And notice how this is drawn. It's not like it's drawn here on the x-axis. This unit here is way above here, above the x-axis up here, and it's drawn at this weird funky angle, right? So this is the first thing that breaks our idea. And if you really figure it out, you could figure this out differently. If you were going to draw the, if you were going to draw this out, right, as an example, you could draw it in a different way altogether. I could draw it that, the force of gravity is hanging down here, and then I could draw the normal force up this way, and then I have something else over here. I could draw that part too, right? Because some component of the normal force, the y component of the normal force, which is at an angle this time, right? The normal force is at an angle, right? The normal force is not straight up and down. That means it's not being countermanded. There's going to be some energy that's leaked from the normal force, right, onto the y-axis plane. That's what's happening, right? There's the x component is not being taken care of. It's not in balance anymore, right, because of the angle. So, and usually there's some kind of critical angle that we're raising the platform in order for us to move the object across the slope, right? Whatever that critical angle is. Okay. And so we can start analyzing it. I didn't want to give you the whole thing, but if you notice that the sum of all forces across the x-axis is mg sine theta, right? Which is equal to mass times acceleration across the x-axis, if you think about it, right? And then the sum of all forces across the y-axis are in balance because my car is not sinking into the platform and the car is not flying up, right? So it's the car is in balance. We can say that we don't care about the y-axis because the car is not sinking into the platform, right? And if you think of it that clearly, then all you care about is the acceleration across the x-axis, which is g sine theta, gravity times sine theta at the end of the day. Once we know that, because we don't care about the mass, because mass, my friends, is irrelevant in this case. It could be 10 tons. As long as it's a frictionless surface, it's going to slide down the slope. All we care about is g sine theta, right? So whatever gravity is times sine of the angle. If the angle was 30 degrees, if that was the thing, and that would be the, we have gravity, 9.8 meters per second, and we can find out the acceleration across the x-axis that way. Are we good with this? I know it's kind of a little bit abstract, right, from this perspective, but you're going to see this problem, and you already have this problem on your assignment. Assignment 2 has this problem, just a loot crate, okay? So I'm giving you hints on how to solve it. All right, next one. So I'm giving you different cases, okay? So that way you've seen different ones. Now this one is also part of your assignment, right? There's one part that's frictionless, the top, and this part is the part on the bottom, right? In some ways. But there's not, blocks don't push each other here. Blocks, there's no block. So what happens when there's two blocks, mass 1 and mass 2, where mass 1 is greater than mass 2? If that's the case, mass 1 is greater than mass 2, right? They're placed in contact with each other on a frictionless horizontal surface, right? As you can see here, right? A constant horizontal force is applied on mass 1, right? As shown. Find the magnitude of the acceleration of the system, right? System means mass 1 plus mass 2 together, right? Because at that particular point in time, mass 1 and mass 2 are touching. You can see the whole mass of the system as one mass, one particle, right? Whatever mass 1 and mass 2 are, right? And especially if mass 1 is greater than mass 2, okay? So it didn't start apart. We're not talking about collisions. We're just talking about the two things are touching, and I'm pushing the bigger mass with a force of energy, right?
The center of gravity and like sort of toward the edge of this.
Something, yeah, almost like right here, because you're looking at almost like the center of mass, maybe over here, because it's like there's more mass on this side than this side, so the center of gravity is going to be here. But notice what they can do. You can actually draw, and it's color-coded here so you can see it, right? You have two free body diagrams. One free body diagram for, the larger mass, and one free body diagram for the smaller mass, as an example, right? And you can see that you can draw the normal force number 1, which is the normal force on the y-axis here, and the normal force 2 on the y-axis, and then they're countermanding the force of gravity for mass 1 and mass 2. These things are being canceled out. And you can see that there's some kind of force. It says, P21 from 2 to 1, and from P1 to 2, those two things are hitting each other, but we're getting only force from one direction, which is the force from the left side of this object. So it's going to push the object to the right if the force is large enough to move both masses. That's what's happening. So again, we analyze it, and we can say that the force across the x-axis, sum of all forces across the x-axis, which is equal to F, must be equal to m1, mass of 1, plus mass of 2 times acceleration across the x-axis, and therefore we can say that the total acceleration across the x-axis is equal to F, the total force, over both those masses, right? And that's how we can find out the acceleration, okay? If we were looking for the total acceleration. And what if you didn't have enough force to move the masses? You'd have 0 acceleration or something negative, right? But typically we don't have a negative force unless we show a free body diagram would look different. Yeah. And then we'd have a different approach. All right, so that's multiple objects. Sometimes we also get into situations like this, right? Like I said, guys, this is the most complex part of what we've done so far because there's so many things to think about. I'm glad that you think so. Some people won't find it this way. Okay, how about this one? So we want to draw 2 free body diagrams to this one. We have M1 and M2. Remember, each mass is considered a particle, so we have to do free body diagrams separately for each one, okay? So here's M1. We can see that there's a free body diagram here. We have a tension across this wire here. And we have M2, well, we have a tension across this wire, right? And we have this situation. We know that if this isn't moving, guess what? They're in equilibrium, which means the tension across the wire 1 and the tension across the wire 2 somehow are supporting the system in place, so it's in equilibrium. And we don't care about this wire here. We can assume that that is like, I don't know, infinite. All right, we don't care about that. Remember we said we don't care about that part. We draw the free body diagram. We want to solve for unknowns as an example, and we start putting some stuff down, right? So if we vary the masses as an example, we can see that there's more tension on one wire than the other, right? Because the tension on both wires are going to be slightly different because of the masses, right? But we know that those two tensions somehow are going to be in balance. We know, right? The tension across the wire versus the mass that they're holding up are going to be enough so that the tension and the mass are going to be in balance somehow, right? And also, we got to think about that going back up to here, that the length of this wire is also very important. We're going to find that out later on as well. Because the magnitude of this line is a lot more than this one, okay? When we have this kind of situation, you might have multiple objects. Am I going to give you this kind of question? And does it make any sense for game? Hell no. You're not going to see. I'm showing you this thing, but I'm not going to give you typically types of questions this way, right? Because in a game, I mean, unless you're going to do some kind of pulley thing in the game and you want to make it realistic, how does that make any sense, right? What was that? You probably would, right? So I probably wouldn't give you this Atwood's machine, but I want you to know about it, that these are in real physics. They use experiments to understand the tensions and all that kind of stuff. Same thing here. You have some kind of pulley, but now you have an object that's on some kind of a grade or a incline. And what do you do here? And again, if I was going to draw the free body diagram, you can draw one for mass 1, which is this one. That's the free body diagram for this one. And this is the free body diagram for this one, just like it was on an inclined plane, right? And you know that somehow, if it's in position and it's equal, then the total forces on this one, if I was going to find the sum of all forces on this one and the sum of all forces of this one, must be in equilibrium, and therefore I can find out the total tension on one wire on the other based on the information that I've been given. Okay? Again, will I give you this kind of question on a test? Chances are not, right? Because we're not going to look at these examples. I mean, it's nice to know about them, but again, just like we talked about in frames of reference, chances are, from an understanding perspective, you don't need to know these things. But this, my friends, is something we need to know about. We're going to be using, we're going to make platformers in our lives, most likely, some kind of, whether it's a 2D or 3D platformer, we're going to make it. Or we're going to, run across the ground. We're going to have a character that runs across the ground. And sometimes it's going to be on slippery ground compared to non-slippery ground. We need to understand the force of friction, okay? So what the hell is friction? It's a resistance or an opposition force that's on a particular plane of action, okay? And typically we have this. These notation is the force. There's two types of forces of friction we're going to be talking about: static force and kinetic force of friction, right? So the static force of friction, and there's the kinetic force of friction. And they have this other thing, we multiply them by something called the friction coefficient. Okay, now where the hell do we get this number from? Tests. That's what it is. You know, they've done a lot of experiments on different kinds of surfaces, and they found there's some standard you know, coefficients of frictions that we can use, and it always multiplies by the normal force. Whoa, what does that mean? But the normal force is countermanding gravity. Now this is where mass is really important. So if I know that my normal force is equal and opposite to mass times gravity, right? Then a larger object, right, that I'm trying to move across a surface with friction it's gonna appear to have a much greater you know, frictional force than a smaller mass. Okay, so in other words, what it says is the static force, right, of friction is less than or equal to the static coefficient of friction times the normal force, and the kinetic force of friction is equal to the coefficient of kinetic force times the normal force. And we'll talk about this. So this is an impeding force. It stops things from moving forward. And we can say that the coefficient of friction depends on the surfaces in contact. The force of static friction is generally greater than the force of kinetic friction. Okay? And the direction of frictional force is opposite the direction of motion, always. Okay? So what does that mean? What is static friction and what is kinetic friction? Can anyone give me an example of static friction compared to kinetic friction? What's static friction?
You have something sitting on a desk, the force you need to overcome to start moving it.
Correct. So if I have an object, let's say a better one for me is I have I don't know, a huge metal safe, right? And a superhero thug, all right, or a supervillain actually, is trying to push this metal safe off of a building to smash the hero, right? I'm just saying. And the metal safe is on a concrete floor, right? And the metal safe might weigh 1,000 kilograms or something like that. And the villain is trying to push this metal safe. Well, the static force is the force that he is trying to oppose. He's trying to move this thing, right? Overcome the static force of friction to move this object across, you know, the surface. What about kinetic force of kinetic friction? What is that? Yes.
Something is moving, kinetic friction is what's slowing it down.
Right. So now the villain actually ends up pushing this thing. He just uses all his force. He pushes it, and it's sliding across the the concrete rooftop of this building, and it's being slowed down. It's being decelerated, if you will. It's being stopped by the friction that's happening between these two surfaces. So what does friction cause from? It's the interaction of the molecules, the atoms, right, that are rubbing against each other, right? In many ways. And of course, because there's energy being applied to this thing, we have, when you rub two surfaces together, a lot of times it causes heat, right, as a byproduct. So you have a lot of heat happening. That's remember, because one of the things we're going to learn this semester is that energy cannot be created or destroyed, right? We have a force of energy that we're pushing, and then the energy's got to go somewhere, right? Part of the energy, when we have an opposing force, is being sucked into the force of friction, right? And then not all of it, the conversion from an energy moving this way to an energy stopping it, it's inefficient. We're going to talk about efficiencies later on. And what ends up happening is some of that energy is lost in terms of heat and smoke and sparks and all those kind of things. The energy isn't destroyed, it's just being dispersed, right? Yes?
Friction is like some portion of the normal force, right?
There's a relationship with the normal force and friction. So we have a coefficient of friction for a surface, right? And we can find out the total force of static friction by taking the normal force and multiplying by the coefficient of static friction. That's how we do it. Every different, because depending on the metal, the different objects, metal on concrete, as a good example, has a specific coefficient of static friction that's different than metal on ice, as an example, right? And we have some charts for that we're going to see in a second. All right, so here's an example now. We're going to draw the free body diagram. We have the force of static friction, right, and we have the force. Notice that the force of static friction and the force that's being applied to this garbage, this garbage can are in opposition. I'm pushing one direction, and the static friction is pushing me in another direction, right? It's pushing in the opposite direction. If I can overcome the force of static friction with the force that I'm pushing with, then the can will move, right? And you can see that there's going to be motion in this direction if I can overcome it. And it says then that as soon as I start moving the can, right, then the force of kinetic friction takes hold, right? Notice the force of kinetic friction is this way, and it's a little bit lower. It's smaller than the force of static friction. And if you notice, where's that? I actually had it in another slide. You can see that that's the case. The force of kinetic friction is equal to this thing, but usually it's smaller than the force of static friction, right? Because if it was the same, if kinetic friction was the same as the force of static friction, it would immediately stop. Right? You have something that's just the same. There's nothing you can do to overcome it. And the next second after you stop applying the force, I've imparted energy, it's going to stop, right? Because there's nothing to stop it from going. So usually kinetic friction is less. The coefficient of kinetic friction is lower than the coefficient of static friction, typically. All right. And we can see that as one force increases, as my force increases, so does the force of static friction. The more force I put on an object, the more static friction I'm going to have as I resist it. Okay. So going back to that, I'm going to go skip to the coefficient of friction here. Here's some coefficients of friction, right? So rubber on concrete, you can see that the force of static friction is 1. That means that you're going to get 100% efficiency from the force of static friction from rubber on concrete. That makes sense, right? Because it's really hard to move something that's, when you have rubber, some kind of heavy object that has a rubber bottom on concrete. Whereas the force of kinetic friction is 0.8, smaller, which means I can still, and when I get going with this thing, if I actually move this thing, it's going to stop fairly quickly. Like 0.8 means that we're very close to 1, which means it's not going to move very far, even if I do end up moving it, right? In fact, anything, it will tip over, right? Depending on where I apply the force, right? I can actually tip an object over. I can't overcome the force of static friction. Like example, a big fridge. If you push a fridge from the top, and if it's too heavy to move on the bottom, it's just going to tip over, right? So steel on steel and aluminum on steel and a bunch of other examples. But take a look at like waxed wood on wet snow, right? That makes sense, right? So it looks like, you know, we have very little friction. You've got like some kind of toboggan. This is a good thing. We're Canadians. We know about these things. Some of us have done tobogganing, right? We get on a toboggan, the force of static friction is very low, like 0.14. That's 14%. If you think about it, it's going to slow us down by roughly 14% on some kind of surface to stop us from getting going. But once we get going, it's even lower. It's going to slow us down, but it's going to take a bit of time to slow us down. And waxed wood that's on wet snow. On dry snow there's 0. Look, it says it's negligible. So we can start going. And this is one case where the force of kinetic friction, right, is actually higher than the force of static friction. So a waxed wood on dry snow, this thing is moving, right? You get on that thing, it's going to go, it's going to fly, right? But as soon as you're on that thing, it's going to slow down eventually. That's kind of the one thing. Metal on metal, lubricated, Teflon on Teflon, ice on ice. You can see that it's different kinds of effects. Am I going to give you this kind of stuff to calculate on a test? Chances are not. Chances are not. I might give you the total newtons. I might say something like, well, if you're going to get one of these things, you might get one question that has, here's your kinetic force of friction, and you need to know this kind of stuff, how to figure it out. I might give you a coefficient of friction, and I want you to find the, you might have 2 coefficients, one of static friction, one of kinetic friction, to find out the total force that's preventing you from moving or whatever. But chances are I might just give you, here's all of the kinetic force. You have this many newtons of kinetic force, right? This many newtons of static force, as an example. And so you don't need to know about the coefficient, right? And in fact, in your game, you're probably going to do that too. right? You're probably going to say, how many forces, what's my force in the opposite direction to stop me from moving, right? Okay. I told you this was a long one, and it is, and I do apologize. But friction is kind of the last part that I want to talk about for the most part. So we have an example here. Okay, so again, this is friction along an incline. The same kind of stuff applies to the incline, but now we have this force of static friction added in the mix, all right? So all the things we looked at earlier with the runaway car and the whole notion of we have mg sine theta as the only force, normally, this part here. But now it's being opposed by this force of static friction. And it'll change the acceleration across this plane a lot more. Notice that there is a corrugated area here. This corrugated area is a reference to the force of friction, that this actual object is not frictionless in this particular case. This is typically how you would see it. Okay, and there's the solution for that, which I'm not going to go into. Although you can see that when you get into the force of static friction is equal to mg sine theta, right? Because mg sine theta is the opposing force, right? If we say that nothing is moving, if the object is not moving, right, then both forces would be in equilibrium. The static friction is keeping the car, as an example, on the slope or the object on the slope without moving, right? That means the force of static friction must be equal to, mg sine theta from that particular, whatever the angle is. Now, there's going to be a critical angle, right? If I keep increasing the angle somehow of that slope, where it's going to be the same as the force of gravity, and maybe it's going to overcome the force of static friction, and therefore the object is going to slip down the slope. And by the way, guys, this is how our tires work, if you think about it. We have some, our tires, and we're going to talk about this again later in the next unit when we talk about circular motion, right? And how our tires stick to the ground because of the force of friction, right? So why do we have banked curves when it comes to entering and exiting the highway? So that way our car won't fly off into into a snowbank or something like that when it's snowy. The bank actually compensates for the slipperiness that you're going to lose, the lack of friction, the static friction. That's right, slides you back this way. And meanwhile, your car is going to tend to want to fly off into infinity, right? So that's where the bank comes into play, right? Now, sometimes if the road has been engineered wrong or hasn't been engineered correctly for bigger vehicles like trucks, that's where you have the flipping over stuff happening. Yeah.
When you have the tire rotating on the road, it's always a different part of the tire just touching the road.
Yeah.
So the tire is technically not moving on the road.
It is moving on the road, but what you're getting is there's a lateral motion, right? Okay. Trying to push the whole car off the road. And the tire, because rubber on concrete has a very high coefficient of static friction, it's 1, right? So it's hard for you to move an object laterally like a whole car. But however, if I put some ice on the road, now it's not rubber on concrete anymore, it's rubber on ice, right? And this is where we get a much lower coefficient of static friction, which means that the car will slip.
But if the tire isn't moving laterally, if it's moving like
forward, same.
Wouldn't that be?
But say that's how tires work, right? So tires work like this. So you have a tire that comes down, and different parts of the tire, right, are having like taking hold and gripping the ground. It's almost like I'm doing this with the ground with the tire. I'm gripping the ground as I'm moving. The tire's moving forward, and parts of the tire are gripping the ground as I'm moving, right? And then when I stop, the tire does this. It stops, right? So it tries to take hold of the coefficient of static friction to slow me down. So when you hear a car skid, right, it means that I'm trying to stop the car too fast, right? And where anti-lock brakes work, or even gearing down or whatever when you're driving, the wheels are trying to turn slower, and so that way, and you might get some slip as well, but you won't get as much as if you slam on the brakes. If you slam on the brakes, what happens is you're hoping that the coefficient of static friction on the ground, in that particular case, is going to slow you down enough, right, so you don't have a collision, right? Again, we'll talk about this next unit, which is next week. The week we come back. Next week, of course, remember, guys, is reading week, right? I know some of you are doing all kinds of other stuff, and you're worried about exams and different projects that are due today or this week or whatever. So I know some of it's going like this above your head right now because you're worried about other stuff. But next week we have a week off, and when we come back, we'll talk about circular motion. All right, so I'm not going to keep going to this. Here's another example. I have a hockey puck on a frozen pond. We're almost done. It's given initial speed of 20 meters per second, so I have some numbers. If the puck always remains, I don't know why it says, it should be on ice, there we go, on ice that slides 150 meters before coming to rest, determine the coefficient of kinetic friction between the puck and the ice. Okay, what does that mean? How does that work? So I've given an initial speed of 20 meters per second, which means what have I done? I've overcome the initial static friction, force of friction. I've already done that, all right? I'm already in motion. So because I'm in motion now, it's not the force of static friction that's taking hold. Now kinetic friction is this thing that's slowing me down, right? So think about it as an acceleration, right? In the negative direction, right? A negative acceleration, right? So again, it says that I start off at 20 meters per second. That's my speed. I have a velocity vector, right? And I have some kind of negative acceleration that's going to slow me down in 115 meters. That's the distance, okay? So how do I figure this out? I draw my free body diagram. I don't know why that did that. I draw my free body diagram. It's just to wake you guys up. There it is. I have my normal force. I have my force of gravity. And then I have this force of kinetic friction that's stopping me from moving in this direction, right? So if I analyze it a little bit, you get to this. You get that the sum of all forces across the x-axis is equal to the negative force of kinetic friction. When we talk about negative force of kinetic friction, which is equal to mass times acceleration across the x-axis, it's equal to that, right? Because remember, the amount of force I'm putting into it is equal to the friction equals to the negative amount of that, right? It's the opposite amount or the equivalent amount. So the force across the x-axis equals the mass times acceleration, right, on the x-axis alone. And then the sum of all forces on the y-axis is 0 because the puck isn't jumping up from the ground or going into the ground, right? We know the puck is in equilibrium on the y-axis. So now that we know that, we can say that the negative coefficient of friction, right, times the normal force, that's what this is. The negative force of kinetic force of friction is equal to negative mu, where mu is the coefficient of kinetic friction, right, times the normal force. That's what this is, right? And you can say that the normal force is equal to mass times gravity, right, which is equal to mass times acceleration across the x-axis. And once you start doing that, you see there's mass on both sides. Just like we said before, mass has no bearing here, so we can remove the mass. Mass doesn't matter, so we just get rid of that mass. Because we can, if I divide both sides by m, mass, then mass is no longer an issue. It's no longer a factor, right? And then we're left with the negative coefficient of kinetic friction times gravity, right, as an example. And then it's equal to acceleration across the x-axis. And that's what we're getting here, right? Okay, and then once we've done that, we're going to do some funky recalibration. I'm not going to go into this right now, but we can figure out that once we've done all this work, that's why I put it out there for you. I'm not going to go and try and prove this, right? But this is true, right? We can see that the mass, so it's the coefficient of friction across on kinetic friction is equal to v velocity x initial squared, right, over 2g across the final displacement, right, the final x position. And if you look at that, you take the initial velocity, which is 20 meters per second squared, over 2 times the gravity times the total distance that is traveled. That's what this is, which is 0.177. That's how you find out the coefficient of friction. That's why, guys, am I going to give you something crazy like this to find the coefficient of friction? Chances are not. All right. I might give you something like, okay, here's the coefficient, here's the total friction, how far does it move? That I might give you, right? But I'm not going to give you this other way because of this crazy formula that when you look at it, you're like, wait, what does this mean, right? This is just kinematics, remember? It's going back to the kinematic formulas that we had before, right? When you look at the kinematic formulas, you get something like this. And if you take these xi's and the xf's and all that stuff, and if you think about this, this is just velocity plus 2 times acceleration, times distance is equal to 0. That's what it means. So when I add my velocity and my acceleration to the distance, I have nothing left, and my velocity becomes 0 at that point. That's what it means, right? That's when I stop. I stop at this point because it's going to stop at 150 meters. That's what it means. And if you look at this without breaking it down, you have this little equation here. Okay. You have this other example of frictions that when it comes to, just to talk about the free body diagrams, notice that there can be many, many forces involved in the sum of forces. Again, am I going to get you to do this, on a test? If anything, I might give you multiple free body diagrams and you say, oh, it's A, or it's B, or it's C. Which one is it, right? I'm not going to get you to draw on the test. And that's really it in a nutshell, I think. I have example questions that we're going to get into in lab. Any questions around this one? So Newton's laws, again, we have these 3 laws, right, that we talked about. We're focusing mostly on the second law of motion, which is, F is equal to ma. And, the other ones we want to know about because it kind of talks about how things move in the real world, right? Especially how things collide. The third law of motion is all around collision, if you think about it, right? Which we're going to get into. But we're not going to talk about too much of that right now. And just to go over my announcements, like earlier, by the way, I'm gonna stop this recording, and then you guys, whoever hasn't had a chance to sign in, you can sign in. But announcements, like I said earlier, are please take a look at that template for the SDL template for C++. That's coming up. Assignment 2, some of this stuff that I've talked about today gives you enough information to start assignment 2. Please start if you haven't had a chance to already. I know you guys are busy with other things, right? But at least form your groups up or keep the same groups, talk to each other and know that you're working on something. And this week there's lab 4, which is at the last part of this PowerPoint, has a bunch of questions. So from slide 77 to 81, I want you guys to do that in class. Today in class. And this week, I'm not going to go over these things with you. I've already gone over the questions. I'm going to pull out my SDL template and start working on with you with Visual C++, right? And Visual Studio, right? I'm going to help you guys with these things. So you're going to have a bit of a work session in lab, but I want to pull out your Visual Studio stuff today and test it out and see what everything means, okay? Because we need to start preparing down the line for what's happening in the 3rd module, which is all programming, okay? So I want to take a look at that stuff with you this week, okay? Just letting you know. And I need to get your feet wet kind of stuff with this stuff because the longer we delay, it's going to make your module 3 undoable, okay? It's going to be tough because, you're dealing with code, and it's not your code, it's my code. So I want you guys to get used to my code. That's why we have to start looking at it now, okay? Any questions? Guys, thank you so much. I'll see you in lab for the first lab this afternoon or this morning, and then Wednesday and Friday. And I'm just going to pull off this. I'm going to stop recording so you can log in.